The story of humanity has always been one of reaching farther than we thought possible. From the first rafts that ventured across rivers, to the ships that braved oceans, to rockets that pierced Earth's atmosphere, we are a species that cannot resist the urge to explore. Today, the frontier is no longer just the seas or skies, but the stars themselves. And yet, the scale of this ambition is staggering. Alpha Centauri, our nearest stellar neighbor, lies over 4 light-years away, nearly 40 trillion kilometers of cold, dark space. With current chemical rockets, such a journey would take tens of thousands of years. That is longer than all of recorded human history. So, if we wish to send a probe in our lifetimes, we must think radically differently. Enter one of the boldest ideas in modern space exploration: laser-sail starshots, gram-scale probes propelled at a significant fraction of the speed of light. The basic concept is deceptively simple, yet breathtaking in scope. Instead of carrying massive fuel tanks, a probe would ride on the pressure of photons, tiny packets of light, beamed from powerful lasers stationed here on Earth or in orbit. Imagine a sail thinner than a human hair, lighter than a feather, and spread wide to catch the momentum of a concentrated laser array. Attached to this sail is a probe weighing mere grams, perhaps the size of a postage stamp, loaded with micro-cameras, sensors, and communication gear. Hit the sail with tens of gigawatts of laser power for minutes, and the probe could accelerate to 1/5 the speed of light. At that velocity, Alpha Centauri would be within reach in just over 20 years. But how does light, which has no mass, push anything at all? The secret lies in momentum. Photons carry momentum proportional to their energy, and when they strike a reflective surface, they impart a tiny shove. Normally this effect is negligible. But with a sail many meters wide and unimaginably thin, and with lasers producing power equivalent to entire power plants, those tiny shoves add up. The result: continuous acceleration with no onboard fuel, just pure energy transmitted from afar. This is the promise of laser propulsion. The idea may sound futuristic, but it has deep roots. The concept of light sails was first seriously proposed in the 1960s by scientists like Robert Forward, who envisioned giant sails pushed by sunlight or laser beams. Science fiction quickly picked up on the idea. Authors imagined vast interstellar arcs carried on beams of light, sails glistening like cosmic butterflies drifting across galaxies. For decades, the notion remained largely theoretical. Building the lasers, creating materials strong enough to withstand the forces, and miniaturizing payloads seemed out of reach. But the last 20 years have changed everything. Advances in nanotechnology, photonics, and materials science have opened the door to possibilities once dismissed as impossible. At the heart of this revolution is a project called Breakthrough Starshot, announced in 2016 by billionaire Yuri Milner, physicist Stephen Hawking, and a team of world-class scientists. The plan was audacious: develop a fleet of tiny probes, each weighing only a few grams, and accelerate them with a massive ground-based laser array to 20% of light speed. With sufficient investment and decades of engineering, the first interstellar mission could happen within this century. Breakthrough Starshot reframed interstellar travel from a distant dream to a concrete research program. Suddenly, send a probe to another star was no longer just science fiction. It became a line item in scientific budgets and a serious subject of academic papers. Of course, the engineering challenges are colossal. Let's start with the sail itself. To be propelled efficiently by a laser, the sail must reflect light nearly perfectly, otherwise it will absorb heat and burn up. Materials like graphene, dielectric films, and nanostructured metamaterials are being explored. The sail must also be incredibly light, with a thickness measured in nanometers, yet large enough perhaps 4 meters across, to catch the beam. Imagine building a sail thinner than cling wrap, yet sturdy enough to survive a blast of energy stronger than any power plant can produce. It's an engineering paradox that requires inventing entirely new classes of materials. Then there's the issue of aiming. A probe traveling at 60,000 kilometers per second will cover the distance from Earth to the Moon in just over 6 seconds. The laser must stay locked on a sail accelerating away at thousands of Gs, across thousands of kilometers of atmosphere. Even slight deviations in alignment could vaporize the probe or send it careening off course into the void. This demands adaptive optics systems far beyond what astronomers use to correct for atmospheric turbulence today. The beam itself may have to be spread across a kilometer-wide array of lasers, synchronized with atomic precision, to generate the necessary power. Communication is another massive hurdle. Once the probe reaches Alpha Centauri, how do we hear from it? At such tiny scales, the onboard power supply might be limited to a few milliwatts from a thin film solar panel or a tiny radioisotope source. Yet the probe must send data back across 4 light-years. Imagine a smartphone trying to call Earth from the other side of the galaxy with a dying battery. That's the communication challenge. Scientists propose using the sail itself as a giant antenna, reflecting Earth-based laser signals back to transmit information. Others suggest distributed swarms of probes, so that even if many fail, a few succeed in returning signals. But perhaps the greatest challenge is survival. The interstellar medium is not empty. At 1/5 light speed, even a single grain of dust could obliterate the probe. Collisions with hydrogen atoms, cosmic rays, and magnetic fields could damage delicate electronics. Protective shielding is nearly impossible at gram scale, so researchers are considering self-healing circuits, redundancy, and swarm tactics. If we send 1,000 probes, perhaps only a handful will reach the target. Yet that handful would be enough to revolutionize our understanding of another star system. Why Alpha Centauri? Because it is close, relatively speaking, and because it is fascinating. Alpha Centauri is a triple star system. 2 Sun-like stars, Alpha Centauri A and B, orbit each other closely, while a smaller red dwarf, Proxima Centauri, drifts nearby. In 2016, astronomers confirmed a potentially habitable planet orbiting Proxima, called Proxima b. It is a rocky world, just slightly larger than Earth, orbiting in the star's habitable zone where liquid water might exist. Imagine sending a probe to a world where oceans may lap against alien shores, just 4 light-years away. For the first time, we could see another Earth-like world not as a dot on a telescope, but as a landscape photographed by a probe that flew there. The potential science is staggering. A gram-scale probe might not be able to carry bulky instruments, but even a small camera could capture images of exoplanets, star atmospheres, and interstellar space. Miniaturized spectrometers could analyze starlight for chemical fingerprints. Temperature sensors, magnetometers, and plasma detectors could reveal the nature of the interstellar medium. By sending multiple probes, we could piece together a mosaic of data that would reshape astronomy. It would be the first direct exploration of another solar system in human history. Beyond science, there is symbolism. To launch a probe to Alpha Centauri would be humanity's first step into the galaxy. The Apollo missions symbolized our ability to leave Earth. Voyager showed we could reach interstellar space. A laser sail Starshot would demonstrate that we can touch another star, that interstellar travel is not just a dream for future civilizations but a project within reach of our own. It would send a message: humanity has begun its journey among the stars. Critics argue the costs may be astronomical. Building a ground-based laser array powerful enough to accelerate probes would require trillions of watts of energy and perhaps hundreds of billions of dollars. Maintaining atmospheric stability for the beam is another hurdle. Others question the utility of sending gram-scale probes when telescopes like the James Webb Space Telescope can study exoplanets in detail from Earth orbit. But the counter-argument is that direct exploration has always offered unique insights. A probe flying past Proxima b could reveal details impossible to capture from across the galaxy: landscapes, weather, even potential biosignatures. Just as no telescope image of the Moon can compare to the photos taken by Apollo astronauts standing on the surface, so too would a probe at Alpha Centauri offer a perspective unlike any telescope can provide. Moreover, the technologies developed for Starshots would ripple across society. High-efficiency lasers, ultralight materials, nanotechnology, adaptive optics, and swarm robotics are not just useful for interstellar probes. They could transform energy systems, medical devices, communications, and defense. As with Apollo, the spin-offs may reshape industries far beyond the original mission. Laser sail research is not just about reaching Alpha Centauri, it's about pushing the boundaries of technology here on Earth. Consider also the philosophical impact. For millennia, we have gazed at the stars and wondered, what if we could send a messenger, a spark of human ingenuity, to another star? What would it mean for humanity to know that we have touched another world not by looking, but by going? Such a mission would inspire generations, unite nations, and redefine our sense of place in the cosmos. Children growing up in a world where interstellar probes exist might imagine themselves as citizens not just of Earth, but of the galaxy. The timeline for such a mission remains uncertain. Breakthrough Starshot proposed that within a few decades, prototypes could be tested. Smaller sails pushed by lasers in the upper atmosphere, then orbital experiments, and finally scaled missions. Perhaps by mid-century, the first Starshot could launch, with data returning by century's end. For a civilization that measures progress in decades, not millennia, that is astonishingly soon. We are on the threshold of becoming an interstellar species. Yet there is also humility in this ambition. A gram-scale probe is not a starship with crew and colonists. It is not the giant arcs of science fiction. It is, in some sense, just a tiny seed tossed into the cosmic ocean. But that seed carries with it our greatest gift, curiosity. It carries cameras to see, sensors to measure, transmitters to speak across light years. In its fragile circuitry lies the distilled essence of our drive to explore. And from tiny beginnings, great things grow. Just as Polynesian canoes eventually gave way to global exploration, so too might gram-scale starshots pave the way for larger, more capable interstellar craft. In the end, the idea of laser sail starshots is both wildly ambitious and profoundly simple. Shine light on a sail, push a probe to the stars. The details are hard, but the vision is clear. Within our lifetime, humanity could send its first emissaries beyond the solar system. The journey will be long, the risks immense, the costs staggering. But the reward is nothing less than a new chapter in the story of our species. We would no longer be confined to the cradle of Earth or even the nursery of the solar system. We would be voyagers of the galaxy, with Alpha Centauri as our first port of call. So imagine it. Decades from now, astronomers gather in control rooms around the world. A faint signal, weaker than a whisper, arrives after 20 years of flight and 4 years of waiting. Data trickles in, an image slowly forms on screens. At first, just pixels, then shapes, then a world, Proxima b, its surface revealed for the first time by a probe the size of a stamp, carried on a sail of light. Oceans, continents, perhaps even clouds swirl across alien skies. Humanity sees, for the first time, another Earth-like world up close. And in that moment, everything changes. We know, not just in theory but in practice, that the stars are within reach. That we are not limited to this single world. That our destiny is written across the galaxies. Laser sail starshots are more than science, they are a dream given form. A dream of exploration, of connection, of discovery. And like all great dreams of humanity, it begins with a single step. In this case, a step so small it weighs only a gram, but so profound it reaches the stars. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.